Taits. I represent University of Southern California. I am a distance education student. I'm working on my master's right now, and I will be presenting to you the AirBooster device. So before I get started, I would like to tell all of you that we have the technology today to travel to nearby planets and nearby moons. With chemical rockets, as a matter of fact, we can get to Mars in about 5-6 months. That's a period that a human being can sustain in 0 G. So it's feasible, it's possible, but there's one major obstacle. And I'll tell you what this obstacle is. The obstacle is the price it takes to deliver 1 kilogram into orbit. Because in orbit, we can construct all the biggest spaceships we want, but until we figure out how to make it cheaper to deliver mass into orbit, space will remain unexplored. Now, right here, I got a couple of vehicles comparison to you. We've got heavy, medium, and light launch vehicles. And you can see, it doesn't matter the size of the vehicle. On average, the price you're going to pay is $10,000 per kilogram. That's a lot of money. So, what do we do to make this price less? Well, there's a couple of things you can do, but the one area that I was focusing on is the launch. When a rocket launch, it undergoes an inefficient process. Why? Very simple. First of all, you got dense air, a lot of friction, a lot of air resistance, especially in the first 10 kilometers of flight through the troposphere. You got a directly opposing gravity vector. The rocket travels in a vertical direction, as you're all aware, and it will waste much more fuel because it has to go against gravity. On the other hand, if it's turned parallel to the surface of the Earth, it will waste much less fuel to achieve the same velocity because you don't have the GT term in your velocity equation. Also, the low velocity, it's energetically inefficient for the rocket because what is it doing at low velocity? It is providing kinetic energy to the propellant that's exiting the rocket engine. You do not want that. You want all the energy of combustion to go into the kinetic energy of your launch vehicle. The most optimal, of course, would be for the launch vehicle to travel at the velocity of the propellant which it exhausts, which is about 4 or 5 kilometers per second. Very fast. So again, at low velocity, it's energetically inefficient. You got high engine back pressure. Again, rocket engines work best in back. That's a simple idea. Everybody knows this. And you got a long spool up. Long spool up is not a problem, but why it is a problem is because all those things combined together bring to wasted onboard oxide. It will be wasted because all of these factors contribute to that, and that is inefficient. That is a lot of liquid oxygen that you're just dumping in those first couple of minutes of flight, and you should not be doing that. Why you shouldn't be doing that? Because there's a much better approach to this. Use a jet engine. Right here I have pictured the Pratt & Whitney F100 afterburning turbofan. Why is it a much better idea? Because first of all, the low velocity is actually better for jet engines because it means reduced ram drag on the compressor. So they actually output highest thrust at lowest velocity and lowest altitude, because at lower altitude you have very dense air, and that is very good for the jet engine. Other factors in the jet engine which are good for this application are the afterburner. It can greatly increase the thrust-to-weight ratio, which will, as I'll later show you, make the jet engine acceptable to be used for rocket applications with several modifications. The variable converging nozzle. This is great because it will ensure that our exhaust expands to exactly the atmospheric pressure. Again, this means the engine will always perform at its optimum level. And of course, the ingested air coupled with a high pressure compressor significantly increases our specific impulse. Rocket engines have specific impulse of 300 to 500 seconds. Air-breathing jet engines, if they combust the fuel 14.7 to 1, I mean that is stoichiometric ratio, you will still have a specific impulse of 2,000 seconds. And that is a lot, and the specific impulse is an extremely important factor in increasing the mass ratio of the rocket and eventually, through the process, increasing the payload capacity. So how are we going to combine this jet engine? I present to you the AirBooster device. Very, very simple device. You have a few modified jet engines surrounding a central body, landing legs, parachute system in the top, interior power system. I will go over that. It's very important to increase the thrust-to-weight ratio of the vehicle, and the kerosene tank. This is a vertical takeoff, vertical landing vehicle. It's reusable, and it's used as stage 0. Launch vehicle is coupled on top of it. I will show you the vehicle integration next slide. Now, a couple of things to say about this. Wi-Fi engines, they provide us active pitch and yaw control, just by controlling the thrust on these different engines. Also, bypasses installed in the afterburner section of these engines will allow us roll control. So this vehicle is going to be extremely stable. I don't need any wings, I don't need any fins. It's going to be light, and I will be able to control motion throughout the whole entire phase of flight. Again, it also has short sonic scoops, because from a mathematical model, I said, don't need supersonic engine. Even a boost to sonic velocity, as you will see, will provide a significant performance increase. And the other different thing, and that's part of the modified jet engine, is that the full afterburner, it must combust the air to its stoichiometric ratio. That's how we must extract maximum amount of energy from the air which we combust. And how are we going to increase the thrust-to-weight ratio? As you know, for rockets, thrust-to-weight is possibly one of the most important things. So what we do is we centralize the power system of this vehicle. The jet engines are stripped of almost everything except the turbine and the compressor and the housing. We don't need the gearbox. We don't need the bypasses. We don't need any fans. It's just extremely simple, no transmission. What we do is each jet engine has a power shaft output to a centralized gearbox. Above the gearbox, this is the starter generator. It is used for both starting the vehicle, spooling up the jet engines, as well as generating power for all the different instrumentation during flight. It's integrated in this avionics. You're going to have all your circuitry, all your guidance, all your navigation. It's all a single axis. Right below this, you have your lubrication pumps. These provide cooling for the jet engine. And below that, you have a centrifugal fuel pump, which feeds directly from the kerosene tank that's positioned right under it. So it's very compact, it's very unified, it's single shaft, making it very, very reliable. And again, this allows this vehicle to have a thrust-to-weight ratio of 6:1. That's just for the AirBooster. We need such a high thrust-to-weight ratio because we need to be able to combust enough air to boost the launch vehicle to sonic velocity before we run out of air in the atmosphere. Next slide, I'll show you vehicle integration. So as you see right here, this is the AirBooster. Right here, this is a standard 40-ton liquid oxygen kerosene launch vehicle. Now it is important to notice that when you stack this vehicle on top of the AirBooster, you must also equip the first stage with an expander nozzle. Why is that? Because the launch vehicle will now start at a much higher altitude. And by starting at a higher altitude, it means there is less atmospheric pressure. So now we can expand our gas more, which will boost the specific impulse of the first stage. And here's another image of the fully integrated stack. As you see, it's very streamlined, very compact. So now you're probably asking yourself, well, how's this going to make it cheaper to put a kilogram into outer space? Well, very simple. In a standard, you have a 40-ton, 2-stage to orbit launch vehicle, and it is estimated that on average you can deliver a 400-kilogram satellite. Now, if we stack this vehicle on top of a 15-ton AirBooster, as I previously demonstrated to you, we allow the booster boosted up to Mach 1 velocity, sonic velocity, to approximately 11 kilometers, as was estimated from a finite difference analysis that I ran on the jet engines. The AirBooster will parachute down to Earth, touchdown burn, lands back on the launch pad, ready for the next vehicle. Now, starting at this point, right here, the launch vehicle will continue on its trajectory, but now that it's starting at a higher altitude, at the sonic speed, it performs a pitch-over maneuver much earlier. What does that mean? It starts gaining downrange velocity, orbital velocity, earlier in the game. This allows it more orbital velocity, which translates into higher payload. And it is estimated, after I run my analysis, that such a vehicle, when boosted, can deliver now a 642 kilogram satellite. That is actually 242 kilograms that are uncombusted in the second stage, and I simply replace them with useful mass of the satellite. So now that you know that we can deliver slightly more mass, approximately 60% to orbit, go to the next slide. Thanks to the FAA, we have some projected value for some small satellites being launched from year 2011 to 2018. Total launches is 20. Now, in the first 10 flights, we're going to charge the same amount, $10,000 per kilogram. Why are we going to do that? Because first of all, we need to pay off the cost of such a vehicle. And such a vehicle is estimated to cost approximately $25 million. But once the vehicle pays itself off, the next 10 flights, now we can actually reduce the cost of kilogram delivered to orbit. And after you do the calculation, it turns out that the next 10 flights done performed with the AirBooster, it will cost $6,230 per kilogram. That is almost $4,000 less per kilogram delivered into orbit. This is great savings, and the most important thing is that this AirBooster is reusable. It will be certified up until 6,000 hours, and with 1 minute burn time, 1 minute flight time, it can be reused for a lot of time. A lot of time. Now there is some prior art to this, of course. Actually, the jet engine launch assist concept, which was developed by a person which was not very familiar with science and mathematics. It's similar, but it's very different because the jet launch assist, there was wings used. He didn't really develop a parachute system for landing. Very, very immature concept. And of course, there's also several reusable launch vehicle concepts listed here, like the X-33, Refly, and GTAD. Again, a lot of these are air launch and cryogenic. So, and again, I'm not using any cryogenic fuel, just simple kerosene. You can get it at any airport. So, how are we going to get? So, of course, if you want to build such a huge device, such an expensive device, you must first start with a scale demonstrator, a prototype. And this is where the USC Space Engineering Research Center comes in. They're developing this lunar entry and approach platform for research on the ground. And essentially what it is a platform consisting of a small Coca-Cola can-sized jet engine, about this big, mounted inside a platform with 4 landing legs. And what we really need to do is equip 3 more jet engines here, and what do you have now? Scale demonstrator of the AirBooster. And also the USC Space Engineering Center has very large solid rockets, and which we can mount on top of this platform to be used as basically the second stage for verification of performance increase. Now, the most important thing about this technology that I'm presenting to you is its future, because its future is what really is going to bring down the cost. And as a matter of fact, in the March 2010 issue of Aerospace America, just literally a month ago, Mr. Buzzing, and I will not read exactly his quote, pretty much said that the DARPA Vulcan engine, which is a mixed cycle engine of jet engine, ramjet, scramjet, he envisions it to be used as an acceleration platform for launch vehicles. And this is exactly what the 3rd generation AirBooster is going to be like. Because the 1st generation, we're basing it on afterburning turbojets. The second one, we're going to have afterburning turbojet ramjet hybrid, similar to the J58, as in the Blackboard vehicle. And of course, the 3rd generation, when you also have turbojet, ramjet, and scramjet, you reach Mach 6 velocity with this AirBooster. It entirely replaces the 1st stage of the vehicle. So, and this can deliver great performance increase.